Just to get things started, I'm going to tinker with Maple a little bit just to give you a visual sense of two topics that are coming up if you're not already into them. One is vector functions and one is vector fields. So a vector function is just a vector, as you've been dealing with, except instead of having constants as components, it has little functions as components. And usually we write these functions with the variable t. And when you build a vector, let's say it has two components, and one of the components is cosine t, and the other component is sine of t, if you let t start to change, you can see that this vector is generating different results for every value of t. So imagine you have a marker or a paintbrush that's stapled, the handle is stapled to the origin, but the other end, the terminal end, is free to move. As t changes, this paintbrush follows the resulting vectors and ends up drawing out a curve. And it turns out that you have already experienced vector functions. We just didn't call them that at the time when we were handling parametric equations. Because if you take a set of parametric equations, like for a circle, x equals cosine t, y equals sine t, and you put them into a vector structure where you have an x component of cosine t and a y component of sine of t, you're going to make a circle. When you take linear functions like x equals 4 minus 5t and y equals 1 plus 2t and maybe z equals negative 8t, if you remember, that generates a line. Take those three parametric equations, plop them into three components, build a vector out of it, boom, you've got yourself a vector function. So a vector function is just a much more concise way of collecting together and using and operating on parametric equations of curves. So Maple has a little feature where you can plot vector functions and see what they look like. So on the screen here, you see a three-dimensional vector curve, the maroon kind of saddle shape thing. It has an x component of cosine t, a y component of sine of t, and a z component of cosine 2t. And t is going to be allowed to change from 0 to 2 pi. So when t is 0, we're sitting at the vector 1, 0, 1. And so then when t changes, the vector changes. And we can actually let Maple animate this figure, and you can see how we sort of move around the curve for different values of t. Now, the set of three little arrows that are on that curve is something that's going to come later, perhaps. It's called a tangent, normal, and binormal frame. In other words, if we were to freeze I said freeze. There we go. If we were to freeze that little mini frame right there, you can see that there is a vector tangent to the curve at that point, a vector that's perpendicular to the curve or normal to the curve, and another vector that's perpendicular to both. It's a little mini three-dimensional coordinate system that moves around the curve. Now that's ultimately what we want to get to in some applications, but to start with, we just talk about vector functions. This is one of them. Sorry for the little jump there. I had to make a quick edit. I tried to do something that Maple wasn't going to let me do, and I couldn't figure out why. In this window here, the way you get to it, you can't see the menu options, but if you have access to Maple, you can go up to Tools, and then look for Tutors, and then look for Vector Calculus, right? And then that's what we're doing now, Vector Calculus. And then you can dial up this space curve, which sounds really cool. So vector function, space curve, whatever it is. In applications, these vector functions can be position functions. Imagine this red curve is the position of an object moving through space. Then guess what the tangent vectors represent? Velocity. And then after that would come acceleration, and that gets you in the mind of, well, we're probably going to have to do derivatives of these things. And yes, we will. The good news is you just do the derivative of a vector function by collecting the derivatives of the component functions. It's no worse than that. Now, while I have this open, I'm going to switch over to vector fields, Normally I don't mix topics in videos, but just out of convenience I'm going to do that. A vector field is different than a vector function. A vector field is a recipe that gives you a brand new vector for every point in space or in the domain. So a vector function is a function of a single variable, like t. Or if you really want to get crazy, it can be a function of two variables. A vector field is a function of the components, or sorry, of the coordinates of the space you're in. So in 3 dimensions, the coordinates are x, y, z. A vector field can have components that are functions of x, y, and z. And what that does is it causes a vector to be created for every point in space. This one happens to be the vector field y, negative x, and z. And so if we go to x equals 1, y equals 5, and z equals 2, we would generate the vector 5, negative 1, 2, right? And we can make these more complicated if we needed to, like y squared, negative x plus 4, and how about a sine of z, like that. Whoops, there's a goofy sign there. And then you can see the different vectors that are produced by that recipe. And this can represent a flow field where the vectors that are assigned to each point in space are velocity vectors, for example. And then what you can do is follow the vectors through the field and get the path of an object that is moving through that vector field. Maple is thinking. So here goes an object which is following the vectors through our vector field. So these are just examples of the visuals of the two creatures that you'll be tinkering with. Vector functions, which are curves in space. This is just another way to talk about parametric equations of curves. And vector fields, which are very, very important in physical applications. These could be gravitational fields, fluid flow fields, electric fields, electrostatic fields, all sorts of cool stuff. So in separate videos, we will look at how we operate with these in terms of actually calculating derivatives and other various things like that.